wild to think about, but the ground we're all standing on right now, it isn't solid. Not really. It's actually moving, shifting, and constantly remaking our entire world. So let's get right into it. This is the amazing story of our restless planet. This really gets to the heart of one of the biggest questions in geology, right? What is this invisible force that's powerful enough to shake entire cities to the ground, thrust up massive mountains, and literally move continents? Well, we're about to find out. And trust me, the answer is pretty epic. So a lot of times, the first sign we get is something sudden and violent, an earthquake. The amount of energy these things can release is just unimaginable. We're talking about the power to crack the very crust of our planet. That's clue number one. And then you've got the sheer explosive power of a volcano. I mean, it's literally spewing molten rock from deep inside the earth. This is another huge piece of the puzzle, right? It's a massive sign that there's incredible heat and pressure bubbling just beneath our feet. And finally, you look around and you see mountains. And let's be clear, these are not just big hills. They are the result of forces so colossal they can bend and buckle solid rock, pushing it miles up into the sky. Think about that for a second. So you have earthquakes, volcanoes, mountains. On the surface, they might seem like totally separate things, but they're not. They are all just symptoms of one single, massive, planet-shaping process. Okay, so let's pull back the curtain and find out what's really going on. All right, here's the secret. You have to stop thinking of the Earth's surface as one single solid shell. That's not what it is. A much better way to picture it is like a giant cracked eggshell, or maybe a huge mosaic of massive, interlocking puzzle pieces. And these giant puzzle pieces, we call them tectonic plates. So what are they exactly? Well, they're these enormous slabs of the Earth's rigid outer layer. That's the lithosphere. And they're basically floating on top of a hotter, kind of gooey layer of molten rock called the asthenosphere. And they are always moving, slowly but constantly. We're talking just a few centimeters a year. Yep, about the same speed your fingernails grow. But that slow, steady movement is the incredible engine that's driving everything we've been talking about. But here's the thing. Not all plates are the same. You've got two main types. First, there are the continental plates. These are thicker, less dense, and they're what make up our continents, the land we live on. Then you have the oceanic plates under the sea. They're thinner, but they're also much denser. And this difference in density, it is absolutely crucial. You're going to see why in just a second. So the big question is, how do all these plates actually interact with each other? Well, it all goes down at their edges, what we call their boundaries. Seriously, this is where all the action happens. It's the zone where the Earth's surface is constantly being created and destroyed. And all that geological chaos really just boils down to three basic movements. First, plates can pull apart from each other. That's a divergent boundary. And when that happens, new crust is formed. Second, they can smash together, a convergent boundary, which is how we get mountains. And third, they can just slide side by side, which we call a transform boundary. That's what creates those massive fault rents, like the famous Sandrias. Okay, let's zoom in on those convergent boundaries for a minute. The crash sites. This is where it gets really dramatic. When two continental plates crash into each other, they're both pretty light, so neither one gives way. They've got nowhere to go but up, buckling and forming these towering mountain ranges like the Himalayas. But when a dense oceanic plate smacks into a lighter continental plate, the heavier oceanic one gets forced underneath. That process creates coastal mountains and volcanoes, like the Andes. It's like this incredible geological battle playing out in slow motion. Now, this whole powerful theory of plate tectonics, it didn't just pop up out of thin air. Nope, it was actually the solution to a mystery that had puzzled scientists for over a century. So let's do a little time traveling, shall we? Let's rewind the clock and check out the origin story. It all kicked off with a guy named Alfred Wegener back in 1912. He was looking at a world map and noticed something that seems obvious to us now. The continents, especially Africa and South America, looked like they could fit together like puzzle pieces. So he came up with this radical idea. Maybe they were once all connected in a single supercontinent, which he called Pangaea. You know what people thought at the time? They thought he was completely nuts. Turns out, he wasn't crazy at all. He was right. Over hundreds of millions of years, Pangaea broke apart, and the pieces started drifting. And this timeline here gives you a sense of that epic journey. You can see the continents just slowly drifting into the spots we recognize on the map today. But Wegener had a huge problem. He had the what, the continents are moving, but he couldn't explain the how. He had no idea what force could possibly be powerful enough to push entire continents around. And that's where the theory of plate tectonics came in, decades later. It was the missing key, the engine that finally explained how his continental drift actually worked. And putting those two ideas together, it completely revolutionized how we see our own planet.
Okay, so this isn't just some big abstract science lesson. It's way more personal than that. These exact same immense geological forces have a direct impact on our everyday lives, especially when it comes to the resources we all depend on.
And what's really fascinating here is that the very same heat and pressure that drive plate tectonics are also responsible for creating things like valuable minerals and fossil fuels. But here's the catch. These are non-renewable resources. That just means the geological processes that make them take millions and millions of years. So, for all practical purposes, once we use them up, they're gone for good. And, well, the way we consume them is becoming a massive problem. Just take a look at this chart. It shows a staggering jump in global oil production in just 40 years. We are burning through these finite resources at a faster and faster rate. And that, well, that's a huge challenge for our future. But there is good news. We get the challenge, and we already know what we need to do. Things like shifting to renewable energy, solar and wind, recycling minerals so we don't have to do as much new mining, and just using more energy-efficient technology across the board. These are all totally critical steps. It's really all about building a smarter, more sustainable relationship with the very same planetary forces that gave us these resources to begin with. And all of this brings us to a final, really cool thought. The forces we've been talking about, they haven't stopped. They're still at work right now. The plates are still moving, the Atlantic Ocean is getting wider every single year, and the Pacific is actually shrinking. So that leaves us with one last fascinating question to chew on. What is this restless planet of ours going to look like in, say, 50 million years?